Hold up your hand. In the blood moving through it, right now there is iron. Not much. About 4 grams in your whole body, enough to make one small nail. But that iron has a history, and the history is strange. The Earth did not make it. The Earth cannot make it. No volcano, no furnace, no natural process anywhere on this planet has ever forged iron in any amount worth counting. It was made somewhere else, long before there was a planet to stand on. Every atom of it was forged by a star, and the stars that forged it are gone. They burned through their fuel, collapsed, and blew themselves apart. And in the fury of those explosions, the iron was made and thrown out into the dark. Some of it drifted for billions of years. Some of it fell into the cloud that became the sun and the earth. Some of it is in your hand. The iron in your blood is older than the earth, older than the sun. You are carrying in your veins the ashes of stars that died before our star was born. This is the story of how that happens. One star, followed from beginning to end, born in a cloud so cold it sits a few degrees above the lowest temperature the universe allows, igniting into a middle age that lasts 10 billion years, then swelling, collapsing, and dying in one of the most violent events nature can produce. It is also the story of the people who worked all of this out without ever visiting a single star, and of the one conclusion they did not see coming. The death of a star is not an ending. It is the only reason you are here. Before we start, one small request. If these long, unhurried journeys through the universe are something you enjoy, please take a second to press like and to subscribe. It costs you nothing, but it tells us to keep making documentaries like this one, and it helps other people who love the night sky find their way here. Thank you. And thank you for spending this hour with the stars. To follow a life that lasts 10 billion years, we first need a way to hold 10 billion years in our heads. So we're going to build a clock, and we will keep it running for the rest of this hour. 10 billion years. The words pass by without leaving a mark, because nothing in human experience is any help with them. So take the entire life of the sun, from first light to final darkness, and compress it into a single human lifetime, 80 years. On this clock, 1 year of the sun's life stands for 125 million real years. 1 day stands for 340,000. The sun today is 4.5 billion years old, which on our clock makes it about 37. Comfortably middle-aged. Steady work, no surprises, roughly half its life still ahead of it. Now place us on that clock. Our species, every human being who has ever lived, has existed for less than one of the sun's days. All of recorded history, every empire, every book, every name anyone has ever written down, fits into the last 3/4 of an hour. In a human life, a long one, 80 full years of birthdays and work and grandchildren last 20 seconds. 20 seconds against a star's 80 years. When you look at the sun, you're not looking at a companion of human history. You're looking at something that will not notice human history. Keep the clock. We will wind it again for other stars, and some of them will burn through their entire existence in what our clock counts as a month. Others will still be running when the clock itself has lost all meaning. But every one of them, fast or slow, giant or dwarf, starts in the same place. And it is nothing like fire. The birthplace of stars is the coldest place there is. Between the stars of the Milky Way drift enormous clouds of gas and dust, so cold and so dark that for most of human history, nobody knew they existed. Astronomers call them molecular clouds. The largest are hundreds of light years across and hold enough raw material to build millions of suns. Their temperature sits around 260 degrees below zero, a few degrees above absolute zero, the coldest anything can be. And they're almost unimaginably thin. Even in a cloud's densest regions, a volume of gas the size of a cathedral would hold less matter than a single grain of dust. Call it a cloud, and the word flatters it. It is a slightly imperfect vacuum, the size of 1,000 solar systems. You have seen one. In the winter sky, below the 3 stars of Orion's belt, hangs the middle star of his sword. Look carefully, and it is not quite a point. It is a smudge. That smudge is the Orion Nebula, some 1,300 light-years away, the nearest great star factory to Earth, and inside it, right now, new stars are switching on by the hundreds. Because cold, thin, and dark as it is, a molecular cloud carries the one thing that matters. Massachusetts. And mass means gravity. For millions of years, a cloud can drift in balance. Its faint internal warmth, just enough to hold it against its own weight. Then something tips it. Two clouds brush against each other. The slow traffic of the galaxy's spiral arms squeezes one. Or, often, the push comes from outside. The shock wave of an exploding star, sweeping through the cloud like a hand closing around it. Remember that push. By the end of this story, it will matter a great deal. However it starts, once a pocket of the cloud grows dense enough, gravity takes over, and from then on the fall feeds itself. The pocket drops inward on itself, and as it shrinks it spins faster, the way a figure skater speeds up by pulling in her arms, flattening the infalling matter into a vast rotating disk. At the center of the disk, matter piles onto matter, and the crush of all that weight drives the temperature up. 100,000 years into the collapse, the center is already glowing. Not from fusion. Nothing is burning yet. It glows from compression alone, the simple violence of falling, the way a bicycle pump grows warm in your hand. This object, a star that is not yet a star, hidden inside its cocoon of dust, keeps contracting, and the core keeps climbing. 1 million degrees. 5 million. 8. And then, somewhere around 10 million degrees, in the buried heart of the collapse, something happens that has nothing to do with falling. The core stops getting smaller. The fire has arrived. To understand what kind of fire, we have to leave the nebula for a moment, because human beings spent 300 years asking that exact question about the star next door, and the answer defeated every one of them until almost living memory. By the middle of the 19th century, science could weigh the sun, measure its distance, and calculate, from the sunlight falling on Earth, exactly how much energy it pours out. The one thing nobody could explain was where the energy came from. The obvious answer was the one in every fireplace. Perhaps the sun was a ball of something burning, coal being the era's best fuel. So physicists did the arithmetic. A sun made entirely of coal, burning fiercely enough to shine as the real sun shines, would burn itself to ash in a few thousand years. Egypt has written records older than that. The fireplace answer was not merely wrong. It was wrong by a factor of 1,000,000. Lord Kelvin, the most formidable physicist of the age, proposed something better: gravity. A sun slowly contracting under its own weight would squeeze heat out of the fall itself, exactly as our collapsing nebula does. Kelvin's mechanism was real physics, and it bought the sun a lifespan of 20 or 30 million years. But by then the geologists were reading a different clock. Rock strata and fossils spoke of an Earth hundreds of millions of years old at the very least, and an Earth cannot be older than its Sunday. The two sciences glared at each other across the gap for half a century. Kelvin never gave in. He also never found the missing furnace, because the missing furnace could not be found in the 19th century. It required two ideas the 19th century did not have. The first arrived in 1905, when Albert Einstein showed that mass and energy are the same thing in different clothes, and that a small amount of mass is worth a staggering amount of energy. The second arrived through the spectroscope, and it came from a doctoral student. In 1925, at Harvard, a young astronomer named Cecilia Payne finished a thesis on the composition of stars. Everyone knew what she ought to find. Stars should be made of roughly the same stuff as the Earth. Instead, her analysis said the stars are overwhelmingly hydrogen, the lightest and simplest atom there is. The conclusion was so unwelcome that a senior colleague, Henry Norris Russell, persuaded her to describe her own result in print as almost certainly not real. 4 years later, Russell reached the same answer by another route, and the field accepted it. The astronomer Otto Struve later called her work the most brilliant doctoral thesis ever written in astronomy. She had found the fuel. The English astrophysicist Arthur Eddington, meanwhile, had already guessed the furnace. In 1920, he proposed that stars run on the crushing together of atomic nuclei, hydrogen fusing into helium, with the small difference in mass paid out as energy through Einstein's exchange rate. Critics objected that the sun was not hot enough for nuclei to fuse. Eddington, not a patient man on this subject, invited them to go and find a hotter place. He was right, though the proof needed one more decade and one more idea. Atomic nuclei all carry positive charge, and positive charges repel. Even at 15 million degrees, the core's protons should never touch. Quantum mechanics showed that, very rarely, they cheat, tunneling through the barrier that classical physics says is impassable. Rarely is enough. In 1938, the physicist Hans Bethe worked out, step by step, the exact chains of reactions by which stars fuse hydrogen into helium. The furnace finally had a blueprint, and it won Bethe the Nobel Prize. So this is what has just switched on inside our collapsing cloud, and what has been running inside the sun for 4.5 billion years. Every second, the sun's core fuses 600 million tons of hydrogen into helium. 4 million of those tons do not come out the other side as matter at all. They come out as pure energy. Every second and a half, the sun converts the mass of the Great Pyramid of Giza entirely into light. And yet the sun is so vast that this furious spending barely registers. In 4.5 billion years of it, the sun has used up about 0.03% of its mass. Something else happened at ignition, and it is the real beginning of our star's life story. The outward push of the fusion furnace rose to meet the inward crush of gravity, and the two forces locked. Gravity squeezes, the fire pushes back, the star holds its shape between them. That standoff is what a star is. Everything that follows in a star's life, every swelling and every collapse, is what happens when one side of that standoff starts to win. For now, the newborn star has reached equilibrium. The dust cocoon burns away, the leftover disk begins quietly assembling planets, and the star settles into the long, stable prime of its life. How long? That depends on a single number, fixed on the day the star is born. And the number works exactly backwards from the way you would guess. Everything about a star's life, how bright it burns, what color it shines, how it will die, and above all how long it gets to live, is set by one thing: how much matter it collected from its birth cloud. Mass is destiny. You would think a bigger star, with more fuel in the tank, would live longer. It is the opposite, and the opposite by an absurd margin, because a bigger star does not burn its extra fuel at the same rate. Double a star's mass, and its weight squeezes the core so much harder that the furnace runs more than 10 times brighter. The tank is twice as large. The engine is 10 times as thirsty. Run the numbers up the scale, and the results turn brutal. The sun gets about 10 billion years of stable life. A star of 15 solar masses gets 10 million, 1,000th as long. The true giants, the rare monsters of 60 and 80 solar masses, blaze with the light of 1 million suns and are dead in 3 or 4 million years. Wind our clock again and feel the difference. The sun lives its 80 full years. The 15 solar mass star is born, burns, and dies in a single month. The brightest giants get about a week. Somewhere in the galaxy tonight is a star that will begin and end its entire existence inside the span our clock gives to one human summer holiday, and it will shine brighter in that week than the sun will manage in 80 years. Now, run the scale the other way, and it gets stranger still. Below about half the sun's mass sit the red dwarfs, small, dim, frugal stars that sip their hydrogen instead of gulping it. They're by far the most common stars in the universe. Of every 10 stars in the Milky Way, roughly 7 are red dwarfs. You cannot see a single one of them with your naked eye, and they will outlast everything you can see. The smallest of them will burn for trillions of years. On our 80-year clock, a red dwarf lives for tens of thousands of years. The model breaks, and that leads to one of the quietest, largest facts in astronomy. The universe is a little under 14 billion years old, and the lifespan of a red dwarf is far longer than that. So in the entire history of the universe, no red dwarf has ever died of old age. Not one, anywhere, ever. Every red dwarf that has ever been born is still burning tonight. The universe is simply not old enough to have seen one finish. You can read this whole hierarchy off the night sky with your own eyes, because a star's color gives away its class. Go back to Orion. At the hunter's foot blazes Rigel, blue-white, a supergiant of some 20 solar masses burning with the light of tens of thousands of suns, already deep into its short, extravagant life. At the opposite shoulder glows Betelgeuse, unmissably orange-red, a doomed giant near its end. It has business later in this story. And scattered invisibly between the constellation's bright stars are red dwarfs beyond counting, too faint to see, which will outlive everything else in the frame. One patch of sky, one glance. The whole span of stellar destiny, color-coded. Astronomers call a star's long, stable, hydrogen-burning prime the main sequence. It is where our own middle-aged sun serves 37 years old on our clock, and it is the least eventful stretch of any star's life, which for us is excellent news, because that steadiness is the only reason a planet nearby can keep liquid oceans for billions of years while life slowly works itself out. But the tank is not bottomless, not even for a careful star. Deep in the core, helium ash has been settling for billions of years, and hydrogen has been running down. On our clock, the sun has about 40 years left of steady burning. Then the standoff at the heart of the star begins to fail. And the first thing that failure produces is not a fading. It is the opposite. The star's dying begins with the most spectacular growth spurt of its entire life. Every star carries the seed of this moment from the day it ignites. Fusion happens only in the core, the innermost few percent of the star, where the crush is fierce enough, and the core cannot restock. However, much fresh hydrogen floats in the layers above, it cannot get down into the furnace. The star will spend its life surrounded by fuel it can never reach. So the day comes, 10 billion years in for a star like the sun, when the core's hydrogen is gone. What remains there is helium, the ash of the whole long prime, and helium at these temperatures will not burn. The furnace goes out. Gravity, which has waited 10 billion years without once letting up its grip, begins to win. The core sags inward under the weight of the star. And here the story takes its first sharp turn, because collapse is exactly what a stellar core cannot do quietly. Falling matter heats. The dead helium core, squeezed tighter and tighter, grows hotter than the living furnace ever was, and that heat floods outward into the layer just above it, a shell where fresh hydrogen still exists. The shell ignites. Now the star has a new furnace, fiercer than the old one, in the wrong place. The fire is no longer buried at the center with the full weight of the star to contain it. It is burning further out, driving heat into the loosely held outer layers, and the outer layers do the only thing they can. They swell. The star inflates like nothing else in nature. Over hundreds of millions of years, it grows to 50, 100, 200 times its old diameter. And as its substance spreads across that enormous new surface, the surface cools, and its light shifts from white gold down to a deep sullen red-orange. The star grows brighter by growing colder, a paradox on paper, but simple arithmetic of a surface now vast beyond reason. Astronomers call the result a red giant. You can see them from your garden. Aldebaran, the orange eye of the bull in Taurus, is a star of roughly the sun's mass, already gone down this road, swollen to some 44 times the sun's diameter, glowing 400 times brighter. Arcturus, one of the brightest stars of the northern spring, is another. When you look at them, you're not looking at a different kind of star. You're looking at the sun's future, and that future is on the calendar. In about 5 billion years, the sun's core hydrogen runs out, and the sun begins to swell. Mercury's fate is not in serious doubt. The innermost planet is engulfed, slowed by the thin, hot gas of the sun's outer layers and dragged down inside, adding its iron to the star that made it. Venus almost certainly follows. Then the sun's swelling surface approaches a small blue world, third from the center. Long before the swelling starts, the Earth story as a living world is already over. The sun has been growing slowly brighter all its life, by roughly 10% every billion years, and models suggest that within about a billion years that gentle brightening is enough to boil the oceans away. The deadline for life on Earth is not the red giant, 5 billion years out. It is a fifth of that. When the giant phase finally arrives, it arrives at a world that has been bare rock for eons. Stand on that rock on the day the red giant sun reaches its greatest. The sun, you remember, covered half a degree of sky. You could blot it out with a fingertip. This sun rises for hours. It is a rippling wall of dim red fire that climbs until it fills a third of the heavens, horizon to overhead, close enough that its surface shows texture. Convection cells the size of whole planets, turning slowly like weather. Whether the Earth itself survives is genuinely an open question. As the sun swells, it also loses its grip, shedding great quantities of gas into space. And as its mass drops, the planet's orbits widen. So the finish is close, an Earth spiraling outward, away from a surface climbing to meet it. Some models let the planet escape, scorched to a cinder but intact. Others, including a detailed calculation published in 2008, conclude that the sun's surface wins the race and the Earth follows Mercury and Venus down. Either way, everything the word Earth ever meant is gone long before the question is settled. Meanwhile, at the center of the giant, the helium core has gone on shrinking and heating, until at around 100 million degrees, it crosses a threshold of its own. Helium, the unburnable ash, ignites, fusing into carbon and oxygen. In a star like the sun, the ignition is not gradual. Models show the core lighting in a runaway flash that, for a few minutes, releases energy at a rate rivaling every star in the galaxy combined. And none of it reaches the surface. The star swallows the explosion whole, so completely that an astronomer watching from outside would see almost nothing change. The helium buys the star time, but helium burns fast and dirty, and there's not much of it. Within 100 million years, or so the star is out of tricks. Its core, now a ball of carbon and oxygen ash, will never grow hot enough to fuse again. A star the sun's mass simply cannot squeeze it any harder. The furnace has no next fuel. All that remains is the parting. It happens with unexpected gentleness. The outer layers, barely held at that enormous distance, are pushed off in slow pulses, drifting away in expanding shells at a few tens of kilometers a second. As the shells thin, they expose the naked core, small and ferociously hot, and its ultraviolet light sets the departing gas glowing like a neon sign, in greens and reds and blues, sculpted into rings and hourglasses and spirals. Astronomers call these objects planetary nebulae, one of the great misnomers of science. They contain no planets. William Herschel, cataloging them in the 1780s, thought their small round disks looked like the view of a planet through his telescope, and the name stuck. Some of the most beautiful photographs ever taken by any telescope are of these death shrouds. The Ring Nebula in Lyra, the Cat's Eye, the Helix, each one a star of roughly the sun's kind, caught in the act of taking itself apart. The beauty is brief. In about 10,000 years, the shells disperse into space, and the glow fades. Set that against our 80-year clock, and the entire display lasts 3/4 of an hour, the same sliver of time that holds all of recorded human history. A 10-billion-year life, and the funeral is over in the length of a lunch break. What the funeral leaves behind, sitting at the center of the fading shells, is one of the strangest objects in the universe. And the first one ever found announced itself long before anyone was ready, as an invisible something tugging at the brightest star in the sky. In 1844, the German astronomer Friedrich Bessel noticed that Sirius, the brightest star in the night sky, does not travel in a straight line. It wobbles, tracing a slow waver across the sky, as if something massive but unseen were swinging it around. Bessel concluded that Sirius has a companion, roughly the mass of the sun, and yet dark. He died without ever seeing it. 18 years later, in 1862, the American telescope maker Alvin Graham Clark pointed a brand new lens, the largest refractor objective in the world at the time, at Sirius to test its optics. Sitting in the great star's glare was a faint point of light. The dark companion was real, and astronomers came to call it, affectionately, the pup. But the real shock waited another half-century, until 1915, when Walter Adams at Mount Wilson finally captured its spectrum, which reveals a star's surface temperature. Everyone expected the pup to be dim because it was cool. The spectrum said it was white-hot, hotter than Sirius itself. Work that through, and the conclusion is absurd. If the pup is that hot yet that faint, it must be tiny, no bigger than the Earth. And Bessel's wobble already fixed its weight, about the mass of the sun, the mass of a star in the body of a planet. A single teaspoon of its material would weigh 5 tons, roughly one adult elephant, balanced on a spoon. Astronomers of the day openly called the result nonsense. It was not nonsense. It was the first white dwarf, the exposed, dead core of a star that had finished the road our sun is on, before Earth had astronomers to watch it happen. What holds such an object up? Not fusion. A white dwarf's fires are out for good. The answer came from a new quantum mechanics, and it is one of its strangest gifts. Electrons' refuse, absolutely, to be crowded into the same state. Squeeze matter hard enough, and the electrons themselves push back, not from heat, but from a law of nature that has no exceptions. A white dwarf is matter compressed to the very edge of that refusal. Atoms crushed shoulder to shoulder, held one step short of oblivion by quantum stubbornness alone. One step short. In 1930, a 19-year-old physics student named Subramanian Chandrasekhar boarded a ship from India to England to begin graduate work at Cambridge, and spent the long voyage doing what physicists do on ships, calculating. He asked how heavy a white dwarf could be before even the electron's refusal failed. The mathematics returned a hard ceiling. About 1.4 times the mass of the sun below it, a white dwarf stands forever. Above it, nothing about a white dwarf works at all, and the collapse goes on to some further fate the equations did not name. For that result, Chandrasekhar was publicly ridiculed by the most eminent astrophysicist alive, Arthur Eddington, the same Eddington who had been so right about fusion, and who now, before the Royal Astronomical Society in 1935, dismissed the young man's ceiling as a mathematical game nature would refuse to play. Chandrasekhar, wounded, left Britain and built his career in Chicago. He was right, and the vindication kept growing for the rest of the century. The Chandrasekhar limit is now settled physics, and it earned him the Nobel Prize in 1983, 53 years after the boat. Hold on to his number. 1.4 solar masses. It is the borderline of the universe's quiet deaths, and it is about to come back with a vengeance. As for the white dwarf itself, its story runs long and calm. It makes no new heat, so it simply cools from white toward yellow, toward orange toward red, over billions upon billions of years, a stellar ember in an ever-darkening room. As it cools, theory says something remarkable happens in its depths. The carbon and oxygen interior freezes, atom locking to atom in a vast crystal lattice. In 2004, astronomers announced that a white dwarf called BPM 37093, its interior ringing with measurable vibrations, appears to have crystallized through much of its bulk. In effect, a diamond the size of a planet. The very end of the road is an object astronomers call a black dwarf, a white dwarf gone completely cold and dark. It is pure theory, and here's why. The cooling takes so long that the universe, at not quite 14 billion years old, has not lived long enough to produce even one. Every white dwarf ever made, anywhere since the beginning, is still warm. That is the fate of the sun and of most stars, swelling, shedding, and then the longest, quietest retirement in nature. If every star died this way, the universe would be a tidier place, and this story would be over. But you already know it cannot be over. There is iron in your blood, and nothing in the story, so far, has made any. Go back to the birth cloud, and this time let the collapsing pocket be greedy. Let it pull in not one solar mass, but 20. A star like this is rare. For every one of them, the galaxy makes thousands of ordinary stars. It spends its short life, 10 million years, a single month on our clock, burning blue-white at tens of thousands of suns' brightness. And when its core hydrogen runs out, it swells like the others into something even the red giants cannot match. A supergiant, a star that placed where the sun is, would swallow the orbits of Mercury, Venus, Earth, and Mars, and reach on toward Jupiter. But the deep difference is not the size. It is what the core can do. When helium ash chokes a sun-like core, the squeeze tops out and the star is finished. A 20 solar mass core tops out nowhere. Gravity there can always squeeze harder, always find the next ignition temperature. And so when the helium is spent and the core fills with carbon and oxygen, the crush simply deepens until, at 600 million degrees, the carbon lights. The star has learned to burn its own ash, and it will go on doing so, ash burning to new ash, each new fire needing a fiercer temperature and giving back less in layer upon layer, until the star is built like an onion, a skin of hydrogen burning over helium, helium burning over carbon, then neon, then oxygen, then silicon, fire nested within fire, 6 furnaces deep. And the pace of it beggars belief. Watch the fuels run out. Hydrogen, the first and best fuel, powered the star for 10 million years. Helium, 1 million. Carbon, 1,000 years. Neon, a handful of years. Oxygen, less than a year. And silicon, the last fuel the universe offers, burns out in about 1 day. The star spends 10 million years on its first tank and 24 hours on its last. In the core's final week, it is running through fuel supplies the way you turn the pages of a book's last chapter. Silicon burning leaves a new ash settling at the very center of the onion. And this ash is different from every ash before it because this one closes the door. The ash is iron. Iron sits at the absolute bottom of nuclear physics. Every element lighter than iron pays out energy when you fuse it. That payment is what stars run on. Iron pays nothing. Fusing iron costs energy, no matter how it is done, no matter the temperature. A furnace that tries to burn iron does not merely gutter. It refunds its own heat into the making of heavier atoms and accelerates its own collapse. Iron is where fire goes to die. So at the heart of the supergiant, an iron core begins to grow, inert, unburnable, fed continuously by the silicon fire above it, like ash piling under a grate. And from the outside, nothing shows. The supergiant fills its constellation as it has for 1 million years. Its light left its surface unchanged. A star with 1 day to live looks the same as a star with 100,000 years. The iron core grows through a day, an hour, a final minute. And then its mass crosses a line you have already met. 1.4 times the mass of the sun Chandrasekhar's ceiling. The border past which the refusal of electrons fails, and nothing about ordinary matter works at all. This time there is no gentleness anywhere in what follows. When the iron core crosses the limit, the electrons that were holding it up fail, all at once, everywhere. And with nothing left to push back, the core does not sag or settle. It falls. An object heavier than the sun, thousands of kilometers across, collapses it up to 70,000 kilometers per second, nearly a quarter of the speed of light. The whole event, from a core the size of a small planet to its final state, takes about a quarter of 1 second. Gravity waited 10 million years for this moment and collects everything at once. In that quarter second, the crush becomes so unspeakable that ordinary matter itself gives up its structure. Electrons are driven into protons, and the two merge into neutrons, the particles that make up roughly half of every heavy atom's nucleus, but now with no atoms left. Just neutrons packed side by side at the density of an atomic nucleus, a single nucleus the size of a city. And each of those countless mergers spits out a neutrino, a ghost of a particle that barely acknowledges that matter exists, and the neutrinos flee the wreck at nearly the speed of light. Then the falling stops, harder than anything stops on Earth. Packed neutrons will compress no further. The collapsing core hits that floor and rings like a struck bell, and the infalling billions of tons above it slam into the rebound. A shock wave forms and tears outward. What happens in the next few seconds is still being fought over inside the world's largest supercomputers, but the leading picture runs like this. The shockwave alone is not quite enough, and it stalls partway out of the star. Then the neutrinos arrive from below, that unimaginable flood of ghosts, and even though each one barely touches matter, there are so many crossing gas so dense that they shove the stalled shock from behind and drive it on. The ghosts push the avalanche over the edge. The star explodes. The numbers of that explosion do not fit inside any comparison, but here is the attempt. In a few seconds, the dying star releases more energy than the sun will produce in its entire 10 billion year life. The debris, most of a star's worth of matter, is hurled outward at up to 1/10 of the speed of light. And for a few weeks, this one object shines with the light of 1 billion suns. In a small galaxy, one death can briefly rival everything else in it combined. Astronomers call it a supernova. And almost everything about that description, the collapse, the rebound, the flood of ghosts, would sound like pure invention, except that nature has performed it in front of us, and we have the recordings. On the 4th of July, 1054, Chinese court astronomers log what they called a guest star, a new light in the constellation we call Taurus, where no star had been. Their records are specific. It shone for 23 days in broad daylight and remained visible in the night sky for nearly 2 years before fading away. Point a telescope at those coordinates today and you find a mass of glowing wreckage roughly 10 light-years wide and still expanding at more than 1,000 kilometers per second. The Crab Nebula, the shredded body of a massive star, 9.5 centuries into its explosion. The guest star was a supernova, and the Chinese astronomers were watching, live, the death we have just described. Keep the crab in mind. There is something at its center we are not finished with. The modern proof came on the 23rd of February, 1987, and it began underground. In a converted mine in Japan, a detector called Kemio Candy 2, a vast tank of pure water lined with light sensors, registered a burst of neutrinos, about a dozen of them, in 13 seconds. Detectors in the United States and Russia caught more, roughly 24 in all. Hours later, astronomers in the southern hemisphere spotted a new point of light in the Large Magellanic Cloud, a small neighboring galaxy 168,000 light-years away. A blue supergiant had exploded, the closest supernova seen since the invention of the telescope. Run the arithmetic on those 24 neutrinos, and the theory checks out with room to spare. For the detectors to catch that many, the explosion had to release around 10 to the power 58 of them, a 1 followed by 58 zeros, carrying almost all the energy of the collapse exactly as the equations demanded. The ghosts even arrived hours before the light, just as they should. Neutrinos escaped the collapsing core instantly, while the light must wait for the blast to fight its way to the star's surface. Some 100 trillion neutrinos from that dying star passed through every human body on Earth. Nobody felt a thing, which raises the question anyone would ask next. When is the neighborhood due? Sooner than the record suggests, in all likelihood. The last supernova seen with the naked eye inside our own galaxy flared in 1604, studied by Johannes Kepler himself, 5 years before the telescope existed. Astronomers estimate the Milky Way should produce 1 or 2 per century, with most of them hidden from us behind the dense dust of the galaxy's disk. Even so, for centuries without a single visible one is a long drought. Somewhere in the galaxy, the next guest star is already overdue, and astronomy keeps a short list of candidates. Look up on a northern winter evening at Orion, at the hunter's left shoulder, and there is the reddish-orange star you have already met. Betelgeuse. It is a red supergiant, roughly 600 light-years away, far down the road that ends in collapse, and it is expected to explode at some point in the next 100,000 years or so. On the timescales of astronomy, that is any minute now. When it happens, Betelgeuse will, for a few months, be the third brightest object in our sky after the sun and moon. by current estimates somewhere near the brightness of the half-moon, compressed into a single searing point, casting shadows at midnight, plainly visible in daytime. It will be entirely harmless at that distance, and it will be the astronomical event of the century for whoever is alive to see it. In 2019, the star abruptly dimmed, and headlines wondered if the moment had come. Careful follow-up showed the star had merely belched out a cloud of dust that hung in front of it like a curtain. A false alarm. But light takes 6 centuries to reach us from Betelgeuse, so there is a real sense in which the star's fate is already sealed one way or the other. It may already have happened. The light may already be on its way. A supernova is the loudest event in the modern universe. But walk into the settling wreckage, years after the flash has faded, and at the center you find the quietest ending imaginable. The crushed core itself, the city-sized nucleus, still there, still spinning. It took astronomy by complete surprise, except for 2 men who called it 33 years early. In 1934, barely 2 years after the neutron itself had been discovered, 2 astronomers at Caltech, Walter Baade and Fritz Zwicky, published one of the most audacious predictions in the history of science. They proposed, first, that certain exploding stars represented an entirely new class of event, which they named supernovae, and second, that such an explosion is the transition of an ordinary star into a body made almost purely of neutrons. Nearly everything just described, the collapse, the explosion, the crushed core ticking in a wreckage, they sketched in a few pages decades before any of it could be tested. Colleagues found the idea somewhere between speculative and absurd. It sat on the shelf for 33 years. Then, in the summer of 1967, at a radio observatory outside Cambridge, England, a doctoral student named Jocelyn Bell was working through the data from a new telescope she had spent 2 years helping to build. Not a dish, but 4 acres of posts and wire, reading the radio sky onto rolls of chart paper. Reviewing nearly 30 meters of chart a day by eye, she noticed what she later called a bit of scruff, a scrap of signal that did not look like a twinkling source and did not look like human interference. The scruff repeated. When she and her supervisor, Anthony Hewish, finally caught it with a faster recorder, the signal resolved into pulses of astonishing regularity. 1 sharp radio, tick every 1 and a third seconds, keeping time like a machine. Nothing natural was known to do that. Half in jest, the team labeled the source LGM-1, Little Green Men. The joke wore thin as the weeks passed and the ticking held. Bell has described the unease of trying to finish a thesis while wondering whether she had intercepted another civilization. Then, just before Christmas, examining chart from entirely different patch of sky, she found a second scruff ticking at its own rate. Then a third and a fourth. For transmitters, in 4 unrelated corners of the galaxy, made no sense for Little Green Men. This was something natural after all, a new kind of star that ticked like clockwork. The press named them pulsars, and within months theorists closed the loop that Baade and Zwicky had opened in 1934. A pulsar is a spinning neutron star, the crushed core of a supernova, whirling with beams of radio energy sweeping from its magnetic poles, a lighthouse in the wreckage, ticking once per turn. And the Crab Nebula delivered the proof. At the exact center of the wreckage of the guest star of 1054, astronomers found a pulsar ticking 30 times every second. The core of the star the Chinese astronomers watched explode is still there, spinning 30 times a second, 9.5 centuries later. In 1974, the discovery earned a Nobel Prize. It went to Hewish and not to Bell, a decision that is still argued about today. So the neutron star came in from the realm of absurd prediction, and it turned out to be, gram for gram, the most extreme object in the visible universe. Hold the numbers up one at a time. It is about 20 kilometers across. A city in the body of a star. A neutron star set down on Earth would fit inside the ring road of a large capital, and it would contain 500,000 Earths' worth of mass, packed to the density of an atomic nucleus. A single teaspoon of its material weighs about 1 billion tons, the mass of a good-sized mountain in a spoon. Its surface gravity runs around 100 billion times Earth's, and the strength of that grip defies parity. NASA once calculated that a marshmallow dropped onto a neutron star would strike the surface with the energy of 1,000 hydrogen bombs. And the spin, 30 turns a second, the Crab's rate, is leisurely for the breed. Some old neutron stars, spun up by feeding on a companion, rotate more than 700 times per second. Stand back from that sentence and look at it. An object the size of a city, heavier than the sun, turning 700 times every second, its equator moving at nearly a quarter of the speed of light. Astronomers use these objects as clocks that rival the atomic clocks on Earth. A few of the breed carry one more superlative. Some young neutron stars, called magnetars, hold the strongest magnetic fields known to exist anywhere. And the standard illustration is only half a joke. A magnetar passing at half the distance of the moon would wipe every credit card on Earth. In December 2004, one of them, 50,000 light-years away on the far side of the galaxy, snapped its own crust in a single flare that measurably ioniced the upper atmosphere of the Earth. A stark wake on a dead star on the other side of the Milky Way, and our sky flinched. That is where collapse stops for most great stars. Caught the last floor above the abyss, held up by the refusal of neutrons as a white dwarf is held by the refusal of electrons. But Chandrasekhar's lesson applies here too. Every refusal has its price of failure. Pile enough mass on a neutron star, somewhere past 2 to 3 times the mass of the sun, and the last floor gives way. For the very largest stars, the ones that die with the heaviest cores, even a ball of packed neutrons cannot carry the weight. The exact borderline is still being pinned down, but somewhere around 2 to 3 solar masses of collapsing core, physics runs out of refusals. No known force, and, as far as we can tell, no possible force, can halt the fall. The collapse continues past the density of a nucleus, past every measurable size, and the core seals itself away behind a boundary from which not even light can climb out. The star has become a black hole, a stellar mass black hole, its point of no return perhaps a few dozen kilometers across, a grave so absolute that not even the light of its own catastrophe escapes to mark the spot. And with it, the inventory of endings is complete. Quiet stars fade into white dwarfs. Great stars detonate and leave neutron stars. The greatest leave black holes. Every star in the sky tonight is traveling toward one of those 3 fates, without exception, and now you know which by watching for a single number, the mass it was born with. But if we stopped here, we would have missed the entire point of the violence. Because the question this hour opened with is still on the table. The iron in your blood came from somewhere. And a supernova's real legacy is not the crushed thing it leaves at the center. It is what the explosion throws clear. In 1957, 4 physicists published a paper that did for atoms what Darwin had done for species. It gave them a family history. Margaret Burbage, Geoffrey Burbage, William Fowler, and Fred Hoyle, in a work known ever since by their initials, B²FH, laid out the case that essentially every element heavier than helium is manufactured inside stars, and that the periodic table on a classroom wall is not a list of ingredients the universe started with. It is a production record. The universe started with almost nothing. The Big Bang furnished hydrogen, helium, and a trace of lithium, and then the cupboard was bare. Everything else, every atom of carbon, oxygen, silicon, gold, everything had to be assembled afterwards, atom by atom, in the only furnaces hot enough for the work, the cores of stars, and the explosions that end them. Hoyle had already produced the theory's signature prediction. In 1953, he was wrestling with a bottleneck. The fusion path to carbon looked forbidden, too improbable to run, and yet carbon plainly exists. So Hoyle reasoned backward from that plain existence. The carbon nucleus must have a hidden property, a precise resonance at a precise energy, that greases the reaction, or there would be no carbon and nobody to wonder about it. He pressed Fowler's laboratory at Caltech to look. They looked. The resonance was there, within a whisker of where Hoyle said it had to be. It remains one of the only times in science that someone predicted a fact of nuclear physics from the fact of their own existence. So the great dying stars are factories, and the layers of the onion are the production lines. The oxygen filling your lungs right now was fused in the bellies of massive stars. By weight, is most of you, nearly 2/3 of your body's mass, locked into water. The carbon in every cell of your body, about enough to fill 9,000 pencils, was made by the helium fire, through Hoyle's resonance, in stars now long dead. The calcium in your bones, the silicon in every rock and every microchip, the sulfur, the neon in the signs, cooked in the deep shells of supergiants and in the storm of the explosions themselves, then thrown into space at 1/10 of the speed of light. A supernova is a delivery as much as a death, about a sun's worth of freshly manufactured matter, addressed to the future. Even the quiet dead take part. A white dwarf with a close companion star can siphon gas from it, creeping upward in mass toward the one number that rules this hour, 1.4 suns, and on reaching it the whole dwarf ignites at once and detonates, a second kind of supernova that leaves no remnant at all. Those detonating white dwarfs are the galaxy's great iron foundries. Much of the iron in your blood, perhaps most of it, was forged in the last second of a star that had already been dead for 1 billion years. And the heaviest elements needed the rarest event of all. For decades, the origin of gold was a genuine open problem. Ordinary supernovae did not obviously make enough. Then, on the 17th of August 2017, detectors on Earth caught gravitational waves, ripples in space itself, from 2 neutron stars spiraling into each other in a distant galaxy, and telescopes swung to catch the aftermath glowing in the dark. The light of that collision carried the unmistakable signature of freshly minted heavy elements, and by one estimate the single event forged dozens of Earth masses of gold and platinum. 2 dead stars, the crushed cores of 2 ancient supernovae, met after billions of years and finished the periodic table between them. Most, perhaps all, of the gold in a wedding ring was made like that, the debris of colliding dead stars, and no one has ever found a cheaper way to make it. The astronomer Carl Sagan liked to say that we are made of star stuff. 70 years of nuclear astrophysics stand behind the sentence, and it was never poetry. It was inventory. Count your atoms one by one, and most of them are hydrogen, and those are the original article 13.8 billion years old, forged in the first minutes of the universe itself. Effectively, every other atom you own came out of stars. You are by mass, mostly stellar ash, arranged for the time, being into someone who can hear that fact. One question remains, and it is the one that closes the circle. The ash was thrown into space. How did it become you? Follow the debris of the explosion outward. For thousands of years it plows on, a shell of glowing shrapnel like the crab, sweeping up the thin gas between the stars, gradually slowing, spreading, cooling, fading. Given a few 100,000 years, it loses itself entirely, its atoms dissolving into the great cold clouds that drift between the stars. That is, the molecular clouds. The nurseries, the place this story began. And the returning debris does more than enrich the clouds. Recall how our clouds collapse was triggered. Often, the push comes from outside, and the sharpest push in a galaxy is a supernova shockwave. The blast that scatters one star's ashes into a cloud can be the very blow that starts that cloud collapsing into new stars. Death sows the field, and death plows it. This is not speculation about our own origins. The evidence is in the ground. Certain meteorites, unaltered leftovers from the solar system's construction, carry the decay products of a radioactive form of aluminium that dies away within a few million years, atoms that can only have come from a massive star, most likely a supernova, shortly before the solar system formed. Many scientists read that as a fingerprint. A massive star died in our neighborhood 4.5 billion years ago, salted the local cloud with fresh elements, and may well have provided the shove that started the collapse. The sun, in other words, is a second-hand star built from the recycled ashes of earlier generations, and its planets were built from the same shipment. The Earth is a supernova's estate, settled. So the wheel turns. Clouds collapse into stars. Stars burn, die, and return their substance, upgraded, to the clouds. And the clouds build again. The Milky Way turns its material over patiently, birthing on average a few new stars every year, each generation born a little richer in heavy atoms than the one before. It has turned that wheel for 13 billion years, and it is turning it tonight in Orion, 1,300 light-years over your head. It will not turn forever. The gas is finite, and slowly, over spans that dwarf even our compressed clock, the galaxy's raw material runs down. The bright, fast stars will become rarer. The future belongs to the patient. Those red dwarfs, the small frugal stars that have never yet died, will still be burning steadily when the sun's white dwarf has cooled toward darkness, and they will go on burning for trillions of years, the last lights in an aging universe, tended by no one. The universe is not in its evening. Measured by its stars, it is barely past dawn. Hold up your hand one more time. The 4 grams of iron are still there, still doing their patient work, carrying oxygen made in one dead star through a body built of carbon made in another. Every one of those iron atoms was forged in the fire of a stellar explosion, the death blast of a giant, or the final second of a detonating white dwarf. Every one rode an explosion that outshone a galaxy. Every one drifted through the dark for longer than the Earth has existed, fell into a collapsing cloud, and was buried in the 3rd planet of the new star, and waited 4.5 billion years, and became, for a little while, part of person. The Earth never made a single atom of that iron. It never had to. The stars had already done the work, and died doing it, and handed it on. That is the life and death of stars. It is also, atom for atom, the story of you.